Good morning, everyone. My name is Umar, and I am a PhD student at UWA. My work is on remote beehive health monitoring, and my PhD supervisors are Gino, Adrian, Rachel, and Amitava. I will start with a quick introduction of electronic beehive monitoring systems. These systems consist of electronic sensors which are placed in or around a beehive. The data they collect is communicated to a storage and where it is processed to extract some information, and that information is accessible to the beekeeper via a user interface. There are two major aims of electronic monitoring: cost effectiveness and better bee care. And yes, they are in this order. If I make a claim that my system can improve the health of the bees by 10%, some of the beekeepers may be interested. But if I make the same claim about profit margins, every beekeeper will be interested. So, for those who are working in this area, it is very important to strike the right balance between these two. Design and development of monitoring systems is a multidisciplinary area. What we are trying to do is improve the long range communication capability of these systems at lower cost and improve the artificial intelligence to provide better bee care. Unfortunately, most of the commercial systems available do not work in Australia because of communication problems. We have designed our own system from scratch, and the sensors and features we have used generate very little amounts of data. This helps us reduce the running costs for these systems. Today, I will be presenting some of the functionality that we associate with a good hive monitoring system, the advantages and disadvantages that are associated with these systems, and design challenges faced by the researchers working in this area. I will also present some of our results. What I will not be presenting is an analysis of existing commercial monitoring systems. Different systems target different customers with different needs. They use different communication modes such as 4G, Wi Fi, and satellite communication. And there is a huge variation in the types of sensors used and the price tags. So, this is like comparing apples with oranges, which we want to avoid. So, what is a good beehive monitoring system? It actually complements the needs of beekeepers, and beekeepers have different needs. Some want to maximize the honey production, some want better value for the pollination services they are providing, and some want to prevent diseases or avoid colony collapse. A good monitoring system is able to do all of these. It also requires little to no servicing. It has long life sensors and it is very energy efficient. With a small solar panel, there is no need to replace the batteries at all. It is also able to handle long distance communications and update itself over the air. This means there is no need to pull it out of the service to update the software. A good beehive monitoring system also improves with time. This does not mean that the hardware improves, but actually the interpretation of sensor data does. This is something that is achieved using artificial intelligence, in our case, machine learning. So, how does machine learning work? Let's say we are collecting sensor data from a hive. At the same time, we collect the beekeeper assessment from the hive, which contains information such as health of the queen, the bees, and the brood. And all this information is fed to a machine learning model. This machine learning model tries to find a relationship between the sensor data and the beekeeper assessment. This is called training. And if a machine learning model is trained properly, it is able to generate beekeeper like assessment just based on the sensor data. A good beehive monitoring system also does not interfere with the bee activity. There are no obstructions at the hive entrances, and the bees are able to move in and out freely. It takes up very little space in the hive, especially in the brood area, and the heat, light, and radio frequency emissions from these systems are not harmful for the bees. The major problem with existing monitoring systems are the high costs. Not just the costs that are associated with the purchase, but also the operational costs, which includes annual subscriptions and the communication fee. And then we have the scalability problem. If we want to deploy these systems in hundreds of hives, we want the price per unit to come down significantly, which unfortunately is not the case. These systems are not as reliable as they should be. Sometimes they generate false alarms, sometimes they do not generate any alarms at all. Their functionality varies with weather conditions, and the AI, artificial intelligence, even though it has improved a lot over past few years, but unfortunately it is not where it should be. Real-time communication is another problem. For any system that uses satellite communication, the cost of communication adds on two fronts: the money that has to be paid and the power that is used with it. At remote sites, conserving power is very important. The alternative of using cellular network works in a lot of places, but unfortunately not in Australia. Here is the 4G coverage map of Telstra and Vodafone. Telstra is on the left with significantly larger coverage, but still this does not cover a lot of sites used by the beekeepers. The size of these monitoring systems is not small enough, and they can eat up a lot of space inside the hive. The weighing scales which go outside the hive are bulky, difficult to work with, and very expensive. Bees are complex, and setting up a non-intrusive experiment is very difficult. The experimental setup mostly results in an altered behavior of the colony, and the data collected is not accurate. Also, the century-old structure of hives with so many moving parts is not research-friendly. The humidity inside the hive is quite high, and the bees put propolis on any exposed sensors. If we cover these sensors to protect them from bees, other insects in the hive start nesting in there. Unfortunately, most of the researchers in the field do not share the data they have collected. For what little is shared, either the sensor quality is poor or there are not enough details of experimental setup. Then we have a lack of sensor diversity. Majority of the studies focus on temperature and humidity, as these are the cheapest sensors around. The human assessment of hives is essential for improving the performance of machine learning algorithms. Researchers rely on beekeepers for this, and there is no standard procedure for hive assessment. Then there is human element. The assessment of a single hive from two different beekeepers can be very different. The commercial monitoring systems rely upon their customers for assessment of hives using mobile apps. Beekeepers very often use these apps to monitor the sensor data from hives but do not provide the feedback. The absence of this feedback is a major reason why the AI in these systems is not improving as it should. Because of intellectual property issues, commercial manufacturers do not collaborate with the researchers in academia. Researchers in academia depend upon masters and PhD students for this research, and with the limited time they have, it becomes very challenging. Most of the students start from scratch and spend a lot of time reinventing the wheel. There is a need for systematic research in this area where people can build upon what others have already done. The sensor system we have designed can communicate using LoRaWAN, Long Range Wide Area Network, and NB-IoT, Narrow Band Internet of Things. LoRa has a range of around 10 kilometers and is free to use, where we have LoRa gateways available, like here at UWA. For remote sites, we use NB-IoT from Telstra. It uses the same cellular structure as Telstra 4G, but has a bigger range. Here we have the 4G coverage map of Telstra, where each tower roughly covers an area of 700 square kilometers. And this is the NB-IoT coverage map from Telstra, where each tower covers an area of approximately 3,800 kilometers. As we can see, it is a significantly larger area, and our sensors are able to communicate from a lot of remote sites. However, this extra NB-IoT coverage comes with a downside: low data rates of around 200 kilobits per second. Also, for LoRaWAN, we are allowed to use 3 seconds of airtime per sensor per day. So to make the most of these long-range communication technologies, we designed our system from scratch, and we process the data using a small microcontroller to extract useful information. We collect around 32 kilobytes of data every 10 minutes and reduce it down to 91 bytes of features for transmission. We are also in the process of building a quality beehive sensor dataset. We are using 9 different sensors, and we are collecting 144 samples per day from 8 different hives. We are also working on improving the AI using machine learning. This is a work in progress, and improving the AI requires a lot of data. We have some of the work that we have done is towards hive weight estimation. Weight data of the hive carries important information. Here is the weight data from one of our hives from 4th of June to 6th of June. We can see that weight between 8 and 9 a.m. goes down as foragers leave the hive in large numbers, and they start bringing the pollen and nectar back. The weight goes up. And after the sunset, the hive loses weight because of the nectar evaporation, and the bees consuming honey to stay warm during the cold nights. We also see some fluctuation in the weight on 6th of June. This is because the weight of the hive is affected by a lot of external factors. In this case, it is the rain. Overall, we can see that the hive weight is going down, something we expect in the winter season. We are using these metallic bulky scales to collect the weight data. They are not easy to work with and are very expensive. All of the commercial beehive scales are. So we thought, what if we can estimate the weight of the hive using the data from other sensors? Just like us having a smart gadget which can monitor all our activity and food consumption and tell us our estimated weight. We decided to put AI to the test. To estimate the weight of the hive using internal sensors, we designed and trained a deep neural network. This neural network requires the initial weight of the hive, size information of the hive, all the sensor data we are collecting, and the weather information. Then it uses all this to estimate the weight of the hive. And, and once it has estimated the weight, it can use the estimated weight to continue with the further estimations. Here are some results from our test set. Actual weight of hive is represented with green circles, whereas the AI estimated weight is shown using orange marks. We can see that on some days the estimations are very accurate. As we collect more data for training, we expect overall accuracy to increase. Here are the results of estimating the hive weight for 58 consecutive days. Blue is the actual weight of hive, whereas the estimated weight is in orange. For the major part, the AI is able to track the weight with very good accuracy. And for the portion where it loses the track, it is able to catch up later on. If we calculate the percentage error between the estimated weight and predicted weight for all 58 days with 48 samples per day, this error never goes beyond plus minus 3%, which for an AI model is quite remarkable. However, this is a work in progress and we are in the process of collecting more data to train and test our model for different environmental conditions, different seasons, bees foraging on different resources, and so on. We are optimistic that our model will still be able to perform reasonably well by the end of this investigation. To conclude this presentation, we are working on the design and development of low-cost sensor systems. We have been able to improve the communication range of these systems using low-power communication technologies. The AI we are working on for weight estimation has shown promising results so far. In future, we will be working on collecting sensor data from weak hives, hives with bee diseases, and train the AI to differentiate between different hives. That's it from my end. Thank you for your time. I'm here to answer any questions you may have.